Recall standing waves. Here's a standing wave on a spring. Recall that we can get the 1 lumper, the 2 lumper, the elusive and mythical 3 lumper, and so on. Been practicing with my shake away. Okay. So we can get 1, 2, 3, 4, 5, right? We have to have an integer number of half wavelengths or else we do not get a standing wave. We can treat the atom in the same way. If we treat the electron as a de Broglie wave, then the particle sets up a standing wave around the nucleus. And so if we visualize this not as an electron that's orbiting, but rather as a standing wave around that nucleus, then guess what? It matches exactly these predictions that Bohr made about the standing wave. And it can explain the discrete spectra of atoms. It's amazing. It works so well. And think about what a standing wave is, right? We can interpret a standing wave as being a wave traveling in that direction and a wave traveling in this direction that are combining in phase, right? We don't really get a sense that this wave is going anywhere. This is not a traveling wave, right? The way that that is, right? There we get a sense that the wave is going somewhere, right? That's a traveling wave. For a standing wave, we do not really get a sense that the wave is going anywhere. But we can interpret this as a wave going that way and a wave going this way, interfering with each other constructively to create a standing wave. So, is the electron orbiting the nucleus? A standing wave is a matter wave going that way and that way at the same time. I don't think this idea of orbiting the nucleus is really that great of a model. It's really a standing electron wave around the nucleus. And much like we had to do here, we have to fit an integer number of, well, in this case it's wavelengths, not half wavelengths. And the reason is just here, our boundary conditions are that end is fixed over there and this end is fixed over here. But our boundary conditions for a circular situation are a little bit more complicated because that wave has to be continuous. And so it's a slightly different condition that we put on the wave. So in the case of the standing wave on the spring, we had to have an integer number of half wavelengths. For the case of the standing matter wave around the nucleus, then we have to have an integer number of wavelengths. 2 pi r is simply the circumference. So this is sort of the classical orbit, which we know is not really that great of a model. We want to interpret it instead as a standing electron wave. And so, this drawing here is a bit simplistic because this is really a three-dimensional standing electron wave, but it helps us to visualize the situation. And this gives us the stationary states of the hydrogen atom. We have the ground state, n equals 1, n equals 2, n equals 3, n equals 4, and so on. And since we can only fit an integer number of full wavelengths around the atom, then we end up with quantized energy. Remember, quantized means not continuous, comes in discrete packages. So, the energy of the hydrogen atom is quantized. That's not all. The radius is quantized. Not any old radius is allowed. Only radii that fit an integer number of wavelengths are allowed. And so we get restrictions on the radii, where each energy level has a different radius. Energies are quantized, as I already said. They all depend on the energy level. And so this 13.6 electron volts, that's how much energy it takes to completely eject an electron from a hydrogen atom. Not only is energy quantized and radius is quantized, but guess what? Angular momentum is quantized as well. Recall that momentum is sort of inertia in motion, and angular momentum is the angular version of that, the rotational version of that. And angular momentum, since we've got the spherical symmetry about the the nucleus, angular momentum ends up being very important for understanding the atom. So angular momentum is quantized, energy is quantized, and the radius is quantized as well. And so just recall that the angular momentum is given by mass times velocity times radius. So hidden in all of this, that means that the velocity is quantized also. But I'm not quite sure what that means for a standing wave. So that's a little bit weird. Here's just a chart. Of course, you don't have to memorize this or anything like that, but here are the first 4 energy levels of the hydrogen atom. Here are the first 4 radii where we expect these things to be. The radius in nanometers, the velocity we might expect, and the energy of these stationary states. So it turns out that fitting these standing waves around the nucleus and using the de Broglie wavelength for that, fitting an integer number of those wavelengths around the nucleus, perfectly yields the Balmer formula. It works out perfect. And so we understand now these different numbers, m and n, we understand these now as the transitions within the hydrogen atom. So recall that the visible spectrum of hydrogen comes from transitions of the hydrogen atom from the n equals 3 state to the n equals 2 state, from 4 to 2, from 5 to 2, and from 6 to 2. Those give us the 4 visible lines in the hydrogen spectrum. The Balmer series, it fits this exactly. And so even though Balmer came up with this just empirically, the Bohr model supports it completely. And this Bohr model now, the Bohr model of the hydrogen atom now predicts the discrete spectrum of the hydrogen atom. So I think this is a great example of what we do in science, right? We can't see an atom. We can't see energy levels. But we create this model in our brain that predicts exactly the things that we do see. And so that's why we trust that model that we've created. And if at some point we find that the model makes predictions that we don't see, that don't jive with reality, then we have to abandon that model. And at this point, the quantum mechanical model of the atom is highly successful. As I mentioned in other lectures, we use this model constantly. Maybe you don't, but scientists and engineers use this model constantly. It's one of the most successful and most used models in all of science. So here is an energy level diagram of the hydrogen atom. Notice that because we've got that n squared on the bottom, the energy levels get closer and closer together as they get closer and closer to the ionization limit. So here we see the ground state, and here we see the excited states, 2, 3, 4. The Balmer series, again, all ends at n equals 2. That gives us the visible lines in the hydrogen spectrum. Again, as I mentioned before, the absorption spectrum all comes from the ground state. Because in general, if you've got a bunch of hydrogen atoms hanging out, they all will be in the ground state. Okay, so this predicts the energy levels of the hydrogen atom. It did not work super well for any other element. Fast forward a decade or so, Erwin Schrödinger introduces his theory of quantum mechanics, which is sort of a complete theory of this subatomic world, including this idea of the wave-like nature of particles. And now the Bohr model was characterized by the single number n. But the Schrödinger model of the atom, the quantum mechanical hydrogen atom, actually we need 4 different numbers to characterize a given state, a quantum state of the atom. So far what we've talked about really is mostly just the energy. But it turns out we need 4 numbers to characterize the state of the atom. The first is the energy, and we've already seen this. So the energy of an atom is determined by its principal quantum number. This is the energy level. And so for the quantum mechanical hydrogen atom, that's given by this formula. The angular momentum is also quantized. And the angular momentum L of the electron's orbit must be one of these values. So h bar, recall, is 2 pi times h. And recall that h has units of eV seconds or joule seconds. these are the units of angular momentum. And so it turns out that the angular momentum is quantized according to this value here. And so we have a second quantum number, and that is L. Little l, is not specifically its angular momentum, but if we know little l, then we can calculate the angular momentum of the electron. The plane of that orbit can be tilted with respect to the z-axis, and only at discrete angles. Again, that angle is quantized. So we find that when we get into the subatomic world, almost every quantity we can think of is quantized, which is just so strange and so not like our everyday experience. So this angle of the electron's orbit can only be at discrete angles. And so that's characterized by an integer m, so that's our third quantum number. And notice that the value of m can only be from negative L to L. Notice that n is our energy level, and our allowed values of L are determined by what n we have. Our allowed values of m are determined by L. And lastly, we have a fourth quantum number. This number m is called the magnetic quantum number. The fourth quantum number is called the spin quantum number. It turns out that electrons have a property called spin, which is kind of like angular momentum. Spin makes us think of a spinning top or something, and initially that is what physicists interpreted it as, but it's more complicated than that, especially since electrons, we're not sure, if we think of electrons as particles, we're not sure if they actually have any spatial extent, right? So imagine a top with no spatial extent. How can you tell it's spinning? You can't. So spin is just an abstract, it's a purely quantum mechanical idea. We can sort of visualize it like the spin of the electron, and maybe spin 1/2 would be rotating like this, and spin negative 1/2 would be like this. That's not a bad place to put your brain, but it's not quite right either. And if that's unsatisfying, it's because it's just a quantum mechanical idea, and you just get used to it. It's not like you understand it in the same way that you understand this experience that you're having as you interact with the human-sized world. With some of these quantum mechanical notions, it's like maybe you never really understand it. You just get used to it. Okay, so we've got 4 numbers now that characterize an electron within an atom. And if we're talking about the hydrogen atom, then these characterize the state of the hydrogen atom. You've seen these pictures in chemistry, if you've taken chemistry. These are, of course, visualizations of the orbitals, the s, p, and the d orbitals. And now we can have a new way to wrap our brain around these. These s, p, d orbitals, they are analogous to our L quantum number. Let's remember what our L quantum number is. Our L quantum number is the angular momentum quantum number. It's the number that characterizes the angular momentum. And so, how are we to interpret these shapes then? These shapes are what the standing electron wave looks like. I just showed you what the standing waves on my spring look like. They look like sine waves. They're not too bad to wrap your brain around, right? But this is the shape of the standing electron waves. I think that's pretty cool. For me, I memorized these when I was in chemistry, and I thought it was really arbitrary and not that interesting. But as soon as I learned that these were standing electron waves, I don't know, now I think it's real darn cool. Okay, so we've got our different orbitals, which are really just characterized by our different L values. So in chemistry, this is kind of how we approach them. In physics, these are L equals 0, 1, 2, and 3. And so now we can characterize the different states of the hydrogen atom like this. Here's the ground state. Our rules for what L values we can have mean that we only have the S state. Moving along, for the n equals 2 state, we can have S and P. For the n equals 3, we can have S, P, and D. And for the n equals 4 state, we can have S, P, D, and F, and so on. Again, we've only shown 4 energy levels here. There really are an infinite number of energy levels allowed. Let's do a quick example. For a hydrogen atom, list all possible states for N, L, M, and M sub s that have E equals negative 1.5 electron volts. Well, let's just see. We're going to use this equation here. Solving for N, we get N is the square root of negative 13.6 eV. I'm just going to go ahead and plug in. This is negative 1.51. And it turns out that this is then the N equals 3 state. So we have N equals 3. Okay, we know that L, let's go back and let's look at these selection rules. Remind ourselves. Okay, how about L? L can go from 0 to n minus 1. So if L can go from 0 to n minus 1, that means L could be 0, 1, or 2. How about M? Well, M goes from negative L to L. So that means that M can be negative 2, negative 1, 0, 1, or 2. M sub s can either be negative 1/2 or 1/2. Those are all of the allowed quantum numbers for a hydrogen atom that has negative 1.1 electron volts of energy.